Hello, my name's Ben and I'm going to be talking today about a new engineering technique that allows us to deterministically create colour centres within diamond. The motivation behind this work is the development of a solid-state quantum technology. The solid-state approach has advantages over other approaches in the fact that we could get a high qubit density, which makes it scalable. Within the solid-state approaches, the nitrogen vacancy centre in diamond has been identified as a viable candidate. This consists of a nearest neighbour nitrogen atom and vacancy within the lattice. It adds this energy structure into the band gap. Here we see a spin triplet ground state, a spin triplet excited state, and a spin singlet excited state. We can treat this as our two-level system and use microwave fields to control the state of the qubit. In order to develop a technology using this centre, we need to be able to reliably engineer them into the material. For this, we need to have a good high yield of single centers, such that we aren't wasting material and processing time. We need to have a good positional accuracy, so that we can engineer control systems around them. And we need good optical and spin coherence, such that we can keep control of the quantum state for a long period of time. There are numerous techniques which have been developed in order to generate these centers within the material. They can be introduced during growth of the crystal through controlling the level of dopants. A commonly used technique is to fire ions at the surface of the material, which straggle and create vacancies. The sample can then be placed into a furnace at high temperature, which allows the vacancies to diffuse around and form the centers. Similarly, electrons can be fired at the surface of the material, creating the vacancies, and then annealed at high temperature in the furnace to allow them to diffuse and form the centers. A fourth technique involves focusing a single pulse of a femtosecond laser into the material, which generates vacancies within the focal volume. The sample can then be placed into a furnace and annealed to create the MV centers. All of these techniques have their advantages and disadvantages and produce reasonable to good quality centers with reasonable to good levels of positional accuracy. However, all of them are stochastic processes, so follow Brownian statistics. Here we present a new technique which builds upon the laser writing technique, but we replace the global anneal with a local laser anneal. So we send a single pulse of the laser in to generate vacancies and follow it by a train of lower energy pulses, which allow these vacancies to diffuse around within the focal spot. Here on the right, you can see an optical diagram. We send our laser through a high NA objective into the material. We reflect the beam off a spatial light modulator, which allows us to get much higher focal intensities through aberration correction. Attached to the optical setup, we have a confocal microscope, which we excite through 532 nanometer light. This allows us to monitor for fluorescence coming from the sample at the same time as processing and continue processing until we see the signal that indicates we have created the center that we wish. Here we have a video which outlines the technique. We place the diamond under a high NA objective. The diamond is nitrogen doped, as can be seen in orange in this video. We send a single pulse of high energy laser light into the material, which has enough energy to break carbon-carbon bonds and knock some carbon atoms to interstitial locations. You can see here vacancies outlined in purple and interstitials outlined in red. We now turn down the laser power and send in a train of lower energy pulses, which allows the vacancies and interstitials to diffuse around but doesn't have enough energy to damage the lattice itself. Many of the vacancies and interstitials will recombine because it's energetically favourable, but some of them will dissociate and some of them will form MV centres. At the moment, this is still a stochastic process. However, we can use our fluorescence monitor to be able to continue processing until we see the signal we want. So we see background fluorescence for the vast majority of the processing time. However, when an MV center forms, we see a jump in the fluorescence level, as can be seen now. What's curious is this fluorescence jumps and spikes several times, and we don't fully understand this process as yet, and then settles down at a stable higher level, which is indicative of the formation of a stable MV center, which we can then stop the processing and use it as a deterministic feedback mechanism. Using this technique, we have been able to deterministically engineer arrays of single MV centers. An example can be seen here. This graph here displays a histogram of autocorrelation measurements with an inset of an example autocorrelation measurement. The G2 values of below 0.5 indicate that these are single centers. The process is highly nonlinear, which has enabled us to get positional accuracies much better than the focal volume of the laser. In fact, we have measured positional accuracies of around 50 nanometers in XY and around 200 nanometers in Z. Here we see a time trace of the fluorescence that we detect from the sample. We see this spiking effect followed by a stable MV signal. We attribute the spiking to the creation and destruction of MV centers during the processing. We measured coherence times of around 170 microseconds. We believe this is actually limited by the amount of nitrogen in the sample, as the sample was around 2 parts per million nitrogen. We plan on now attempting this with lower nitrogen sample. In summary, we have been able to deterministically engineer MV centers into diamond using laser processing and an optical feedback mechanism. This one-step processing allows us to generate large numbers of centers over a large area in a short time scale with good positional accuracy. This is a key step towards the development of a scalable quantum technology within the solid state. I would like to thank you all for listening and look forward to your questions.